In physical science, you learned about two groups of reactive metals on the periodic table. An extremely reactive group, the alkali metals, and a fairly reactive group, the alkaline earth metals. But that word, reactivity, and to say that they're reactive, it just doesn't mean a whole lot unless you actually experience what reactivity is. And that's what this lesson is all about. In this lesson, you are going to experience through two lab demos the reactivity of these reactive metals. Let's review what the properties and structures of these metals are that makes them as reactive as they are and gives them their other properties. It's fitting that we start with the most reactive group of metals on the periodic table, the alkali metals. And the alkali metals have one structural characteristic in common that gives them all of the properties that they have in common, and that is that they all have one electron that is really far away from the nucleus, and that electron is very unstable, just waiting to be ripped away by other atoms. Here's a picture of one of the alkali metals. We're going to take a look at sodium because that's the metal that we're going to observe in our demo. And you'll notice that there's one electron that's farther away from the nucleus than any of the other electrons. That is the electron that gives sodium its properties. Sodium behaves like a metal because it has a whole bunch of those single electrons that are free to move around in sort of a sea of electrons. And that sea of electrons pulls the cores of the atoms together, those positively charged cores, to make a crystalline, solid substance. But here's the deal. With the alkali metals, there's only one electron that each atom contributes to the sea, as opposed to other metals which have two or three or even more. So because there's only one electron from each atom, the alkali metals have some other characteristic properties. For example, they have very low densities compared to other elements on the periodic table. Sodium has such a low density, it's a metal that easily floats on water. As you observe the lab today, you're going to see that that actually happens. Also, sodium has a low melting point, and it's extremely soft and easy to manipulate because the atoms aren't pulling themselves together with just one electron from each atom in the electron sea. It's not very tightly structured. And then finally, that one unstable electron is able to be violently ripped away by other atoms. Let's take a look at how that happens. By taking a look at a different element, we're going to look at an oxygen atom. Oxygen, you may remember, has an atomic core charge of 6 plus, and then it has 6 electrons in its outer energy level. That's the key. It has 6 electrons far away from the nucleus. It wants to have 8 electrons far away from the nucleus, so oxygen can gain 2 more electrons to become stable. One of the places that it can get extra electrons from is sharing with this atom, hydrogen. Hydrogen is sort of interesting because it's near the top of the periodic table. It's one of the few elements that actually only needs 2 electrons in its outer shell to be stable. Hydrogen's so small, it can't even handle 8 electrons in its outer shell, so it's stable with just 2. But it only has 1. There's only 1 electron, period, in hydrogen. So how is hydrogen going to get 2 in its outer shell and oxygen going to get 8? Well, if we have 2 hydrogen atoms and they share their 1 electron with the oxygen atom, you see in water, H2O, each hydrogen is near 2 electrons, and the oxygen now has 8 electrons around the outside. This is a very stable arrangement, a stable molecule. But here's the deal. Sodium is so unstable that it's able to take a stable arrangement like water and completely break it apart and form new substances. What will happen in the case of water, and actually we need 2 water molecules to make this work, but each water molecule is going to break down and make a new substance known as hydroxide. Now, this hydroxide molecule that I just made has all of the original electrons that the oxygen had and the one that the hydrogen contributed as well. Hydrogen bonded to oxygen makes hydroxide, but this is a very unstable molecule because there's only 7 electrons around the oxygen. And if there's 7 electrons in oxygen's outer energy level, it just has to gain 1 more, and it will violently do so. Where can it get that extra electron from? What if it stole it away from one of the sodium atoms? Now, hydroxide has 8 electrons around the oxygen and 2 by the hydrogen. It makes it stable in that way. However, because it gained an extra electron, it's negatively charged overall. It's a hydroxide ion. So what's it going to do now that it's negatively charged? It's not electrically neutral. Well, get this. The sodium that got its electron taken away from it now got rid of that 1 electron in its outer shell, but it lost an electron, so it has a +1 charge. That positively charged sodium ion can join forces with the negatively charged hydroxide, and they can bond together and become electrically neutral as well. Now these atoms are completely stable because they all have 8 electrons, or 2 for hydrogen, in their outer shell, and because they're sharing that negative positive charge, they are electrically neutral as well. But we're not done yet. This isn't just going to happen for just one water molecule. There's actually going to be millions and millions and millions of water molecules reacting, and millions and millions and millions of sodium atoms reacting. I'm going to react another water molecule the same way, and it's going to make a sodium hydroxide crystal over on the right. Now, technically, because there's going to be so much water involved, this sodium hydroxide is going to be dissolved in water. You won't see it as a solid crystalline shape. What about those 2 hydrogens that got left behind that are still over there on the left? Those 2 individual hydrogen atoms can join forces and share their electrons with each other. And if they share that 1 pair of electrons between them, each has 2 in its outer shell, and they're still electrically neutral. Now, that hydrogen gas is going to make an appearance in our demo as well. When you see that this sodium metal appears to light on fire, what's actually happening is that hydrogen gas, which is extremely flammable, is gaining so much energy from the sodium below it that it ignites, and then the whole thing is going to blow up in all directions because the hydrogen will explode. That's what you're going to observe with the alkali metals.
Here I have a can of pure sodium metal. Now, in order to handle this very dangerous substance, I have to wear all of the stuff that we wear to keep safe in the lab. A lab apron, gloves, and goggles. Now, as I open up this container, to emphasize just how dangerous this is, I'm going to show you how it's sealed up when we get it from the chemical company. First off, there's this airtight, waterproof tape that's around the top of the container. I'm going to remove that. Then, inside this airtight metal container, there's a lot of kitty litter to absorb any moisture that might get inside. So I'm going to dump that off into a container. Inside the kitty litter is a bag containing the actual container of sodium. So I'm going to remove that. And then finally, inside this plastic bag is the actual jar of sodium. But that's not all. Inside the sodium container, it's full of mineral oil to prevent the sodium from contacting any moisture in the air at all. So to even get the sodium out, you first need to remove it from inside the mineral oil. And then finally, on the very inside of the container, we have our chunks of actual sodium metal. This is a cube of pure sodium still coated in mineral oil from inside the container.
Now, one of the things I told you about the alkali metals is that they're extremely soft because of their 1 electron and their extreme malleability. I'm going to demonstrate for you just how soft the alkali metals are. This utensil is about the equivalent of a butter knife. It's not extremely sharp. It's going to be able to cut right through this sodium metal to make a smaller piece. And I'm just going to cut into it with the surface of this knife. And notice that I can stick this utensil right into the sodium metal, and it cuts through it almost like it cuts through really hard butter. Now, as you look at the inside of the sodium metal, notice that it's very shiny, like you would normally expect a metal to be. It's not going to stay that way for very long because it's so reactive. It'll react with the oxygen in the air and corrode very quickly.
So at this point, I'm going to put some sodium metal into a petri dish filled with water. This petri dish also has some phenolphthalein indicator added to it. The phenolphthalein will turn a bright, vibrant pinkish color in the presence of a strong base. So you'll notice if there's actually sodium hydroxide being produced. So at this point, I'm going to put the sodium into the water.
Now that you've seen a reaction of alkali metals, let's take a look at what happens with the alkaline earth metals. The alkaline earth metals are located right next to the alkali metals on the periodic table. We're going to take a look at the metal magnesium because that's the one we'll be observing in this lab. All of the alkaline earth metals have 2 electrons far away from the nucleus in their outer shell. Because each atom has 2 electrons far away from the nucleus, each atom contributes 2 electrons to the sea of electrons. More electrons in the sea makes this a much more solid substance. We're going to find that the alkaline earth metals have higher densities, they have higher melting points, they're more difficult to separate the atoms from each other, and they are harder. You're not going to be able to cut them with a butter knife. They're going to be much more solid. And then finally, we're going to find that 2 electrons are much more difficult to rip away from the core than just 1 electron. So these are more chemically stable than the alkali metals were, but they are by no means chemically stable. They are still very reactive. Let's take a look at how the alkali metals would react by looking at our good friend oxygen once again. And I'm going to show you once again oxygen with its 6 electrons in its outer shell. It's 6 plus core. And we're going to bring 2 oxygen atoms together. And I'm going to show you how oxygen forms molecules by making that double bond of shared electrons between them. This is an oxygen molecule, which again, like water, is a very stable molecule. But under the right conditions, we could even force a stable molecule to break apart and react because we're dealing with a very reactive metal substance. So how exactly does that work? Well, in order to make oxygen react with magnesium, I need to add a tremendous amount of energy to the magnesium. In this case, I'm going to do that by adding heat energy over a burner flame. When I do that, what ends up happening is the oxygen molecule will break apart with its 6 electrons in its outer shell, and my magnesium atoms are going to become freed up from their crystal structure. If the magnesium loses its 2 electrons, it's going to form a 2 plus charge. And then those 2 electrons can go over by oxygen, giving it a full 8 around the outside, but also giving it a 2 minus charge. And now I have a 2 plus charge and a 2 minus charge right next to each other. Those 2 ions are going to attract so they can be electrically neutral. And that happens with both of the atoms that were a part of the oxygen molecule before. Magnesium is so reactive that it's going to release a tremendous amount of energy in the form of light. In fact, if you were doing this in person and not through a video screen, you would have to be very careful not to look directly at the light that's being produced by this reaction because it's so bright it can damage your retinas. Now I will show you what happens when you burn magnesium.
This is magnesium metal. Now, magnesium metal is exactly like you would expect a metal to be. It's shiny, it's bendable, which means that it's malleable. It's much harder than sodium metal was. There's no way that I could cut this with a butter knife, but it is very reactive. Now, it's not nearly as reactive as sodium metal. I don't have to worry about this corroding in the air. It's stored in just a plastic baggie, not all the safeguards that sodium had. But if I add enough energy to this, you'll be able to see its reactivity. When I put this into the burner flame that I'm going to light in just a moment, you're going to see that it gives off a bright light. In fact, magnesium metal gives off such a bright light that if you see it in person, you can't really look at it directly because it will damage your retina. You will get a sense of just how much energy is being released as it combines with oxygen in a fire.
Now you've seen the characteristics of the alkali metals and actually observed what it means to be extremely reactive. They react even when you just place them in water. And you've observed the characteristics of the alkaline earth metals, which are still very reactive, but not nearly as reactive as the alkali metals. Remember, these reactivity characteristics are all caused by the way that the electrons are structured around the atoms, and because different groups of elements have different structures of electrons, each group is going to have its own characteristics.